Up guys, today we're going to look at a very simple problem. Actually, we're going to look at the simple pendulum, and we've already looked at the harmonic oscillator and some other examples, but today I just want to look at the simple pendulum and how it reduces actually to the equation of the harmonic oscillator, because the harmonic oscillator is a special case of the simple pendulum, as we will see. And yeah, so let's get going. So let us take a look at how this problem is defined. So basically we've got a wall or whatever, a support, and then we have the pendulum, which basically is a piece of mass with mass m, and then you've got a rod which has length L, and we have to first find the Lagrangian for this problem, and then we will be able to derive the equations of motion. So to solve this problem, let's remind what the Lagrangian is first. The Lagrangian is basically the kinetic energy minus the potential energy, and in this case the kinetic energy is just m times v squared half. So v is the velocity, and if we consider the position of this mass here to be x and y, then the kinetic energy is just m half x dot squared plus y dot squared. So how can we find this the kinetic energy, x dot and y dot, basically? So the way to do it is to drop a line over here and to consider this angle theta. So we're not going to use x dot, x and y as the generalized coordinates, but we're actually going to use theta. Yeah. So so if we have theta like this, then the x coordinate, this guy over here, is just L times sine theta. So we've got x is equals to L times sine theta, and y is just going to be L times cosine theta, because it's on this side, right? This is the y coordinate, and this is the x coordinate, and this is the angle. So yeah. So now to calculate x dot, remember theta is a function of time, so we have that theta is a function of time. And if you want to now find x dot and x and y dot, if we differentiate this, we get x dot is equals to d by dt L sine theta, and this is equals to d by dt of L sine theta plus L times d by dt sine theta. And the reason for that is we're just using the product rule. Now the length of the rod, the length of the master's rod, is considered to be constant, so it doesn't change in time. So this term over here goes to 0. We can cancel this term, and then the derivative of sine theta is just, so this is just L times cosine theta times theta dot, because we're using the product rule. So theta dot, the dot stands for the time derivative. Similarly, we can find y dot. Y dot is d by dt L cosine theta, and that's just minus L sine theta theta dot. And now we want to find the velocity, the kinetic energy. So for that we have to square these two components and add them up. So we've got that m times v squared half is equals to x dot squared plus y dot squared times m half. So this is m half, and now we just take this guy, these two guys, and square them and add them. We've got L squared cosine squared theta dot squared plus L squared sine squared theta dot squared. And now we can take the common factors L squared and theta dot squared out, so we get m half L theta dot squared cosine squared theta plus sine squared theta, and this is just equals to 1. So we get that the kinetic energy is just m L theta dot squared half. So this is the kinetic energy. Now what we have to do is we have to find the potential energy, and the potential energy is just we're assuming that the rod that the support is at a particular height, capital H, right? And then we can calculate the height of the pendulum. So the height of the pendulum, well, the height of the mass at the end of the pendulum is just, so we've got the height and then minus so the potential energy is equals to mg times h minus y, and this is mgh minus L cosine theta, right? Yes. Right. And now to calculate the Euler-Lagrange equations, to calculate the Euler-Lagrange equations, we have to calculate d by dt partial L partial theta dot minus dl by theta dot by theta is equals to 0. So we get d by dt theta dot is just, so this is just d by dt, one sec. So basically this gives me d by dt t del t by del theta dot square by del theta dot, this should be just theta dot, minus partial v by partial theta. And the reason for that is because L is equals to t minus v, and we already calculated that t is only a function of theta dot and v is only a function of theta, right? So we don't need to consider dv by d theta dot and dv and dt by d theta, right? So this gives me d by dt partial t by partial theta dot, that's just ml theta dot squared half, ml theta dot squared half minus, and this is d by d theta dot minus d by d theta, and then the mgh minus L cosine theta, right? So this gives me d by dt, and this just here m and L are both constants and 2 is also a constant, so we don't need to consider it. Let's write this nicely. So this is d by dt ml theta dot minus L sine theta is equals to 0, right? Or in other words, we can write, since m and L are both constants in time as well, we have m times L times theta double dot is equals to L times sine theta, right? This is the equation of motion, and this looks actually very similar to the equation of motion for the harmonic oscillator. The only difference is that over here we don't have theta, in this case we have sine of theta. But if you remember, the Taylor series for sine of theta starts with theta plus higher orders of theta squared, right? So so this is just m times L times theta dot is approximately equals to L times theta and theta double dot. So this is the equation for for the this is very similar to the equation of motion for the harmonic oscillator. The only difference is that for the harmonic oscillator we have a minus over here. Here we don't have a minus sign because we chose the height of the pendulum to go in the other direction, right? So the positive y direction, we said the positive y direction is over here, and this is the negative y direction, and we therefore had that over here we had a minus y over here. But other than that, it's actually very similar to the harmonic oscillator, and it has very similar solutions. So yeah, that's it. This is the explanation, the derivation of the equation of motion for the simple pendulum. Next, there's going to be some more interesting things coming up. So far we have only looked at examples where there is only one mass. So for example, we had the gravitational field, the harmonic oscillator, and the simple pendulum. Now I'm going to take a look also now at two examples where we're going to have two masses or more degrees of freedom actually, and that'll become more interesting. So stay tuned, and please subscribe if you're interested in more of this content, and wish you all the best. Bye.